equation psi nu, where nu is unknown, equal to eta has solution, and this can be given by, and mu is given by and you also have see, whenever eta is not equal to 0, nu equal to 0, and otherwise so this is the result that one can do. Okay, so you have the unknown taken as nu, and psi is assumed to be not equal to 0. Then when eta equal to 0, you get nu equal to 0. When eta is not equal to 0, then nu is, in any case, nu is given by eta divided by psi. Or this is how you designate this. Okay, so you get this is not equal to 0. In particular, we have the multiplicative inverse of okay. Therefore, the consequence of this is that R is also, the consequence is that the consequence of this result R, if you remove the 0 element from it, U, which is commutative, okay. So what do you need for this to be a multiplicative group? Because 0 cannot be beat. Okay. because all elements in are slash 0. It is the complement of 0 has a multiplicative inverse. Okay, so that particular set is closed with respect to multiplication. That's the first thing. That is, multiplication is a binary operation on r slash 0. Secondly, it is associative, it is commutative, and every element has a multiplicative inverse. Okay, and the identity element is there, namely one is there, one is the identity element, and then now all the required properties are satisfied. So it's a multiplicative. And we have already seen that R itself additive with 0 as the identity. So you have addition is a binary operation on R, and it is a group with a 0 as identity element. It is associative, which is commutative. 0 is the identity element with the property that psi plus 0 equal to psi for every psi belonging to R. That we have seen with respect to addition. Or in other words, what we are saying is that, and it has every psi has an additive inverse element which you denote by -1. Okay, so you have got this equation psi plus x or nu equal to eta for this is something that has eluded our considerations earlier, because we are keeping to R plus, you are keeping to Q plus, you are keeping to natural numbers. And only when 0 came in, you had the identity element coming in. And only when the negatives came, you had the inverse elements coming in. Whereas multiplication, as regards to multiplication was concerned, R plus itself satisfied this particular condition, namely it's a multiplicative group with identity element as 1. Okay, so when we extend that, one remained or one continued to be the multiplicative identity element. Okay, and you also observe that with regards to or with respect to multiplication, you had to throw away 0 from that class to get this. And then with all the interactions that we have mentioned, this is what it follows to. There are two binary operations, addition and multiplication, and then it has got a split structure. Okay, 0 happens to be the additive identity element. 1 is the multiplicative identity element. And then you know that R/0 is a multiplicative group, R is an additive group, and then you know the distributive property, etc. And moreover, you also have with the order relation, R is a an order Okay, so that's another property. An ordered field in the sense that there is an order relation superimposed on this field with the properties that we have listed out in the interactions of the order relation with addition, the order relation with multiplication. All those properties are such. Okay. Then of course you have the Archimedean property, that is the property. What do you mean by Archimedean? Archimedean is this. That is, you take R sine theta R. Is a positive element. Then there exists n belonging to such that okay, this is a very important problem. That beta is greater than 0, and for any psi and eta belonging to R, this property is there. This is what's called the Archimedean. Okay, you see that the other things that we have proved is that Q is equal to, what is it? Q minus union 0, Q plus. Q plus we have already defined. Now what is Q minus? An element X is in Q minus, or an element P belongs to Q minus if mod P that's the condition. Then with this you can prove that Q is also an Archimedean order field. Therefore, Q is a subfield of R. You see the operation that you have on R, addition, multiplication and order relation. When restricted to Q will simply reduce to the same sort of operation that we had on Q. We had it on Q plus and then extended to Q, the whole of Q, that is extended to Q minus and 0, etc. Okay? So this is the picture, the final picture that is emerged. We started with n. Z. Z is the set of all integers. Q. And moreover, what one can prove is that R has the additional property that R is in the sense that is every bounded satisfies as least upper bound. It satisfies the least upper bound property. Okay. So that in fact takes the holes. So we found that we try to list it out, what place all the rational numbers on the real line. You had 0, you had 1, 2, etc. 1, 0 and 1 are fixed on this line. Then you see that every point on this has an address given by a real number. That's what it turns out. Okay? Right? So you have got correspondingly -1, -2, etc. And these set of numbers are what we call the integers. This is designated by Z. And Z still has the property called the nextness. Okay. Z has the nextness property. That means given any element of Z, there is an element lying next to it to the right as well as to the left. Okay. So given you have two elements, or any Z belonging to n belonging to, and in between n minus 1 and n, or in between n and n plus 1, there is no other element from Z. Now this is what we mean by nextness. Okay? But the moment you go to rationals, this property is lost. Okay? Given a rational number, you cannot talk about a rational number lying next to it, either to the left or to the right. Okay? So that's one of the important things. about the freshness.